the two types of filters has been explained, and using this I can show you the one of the statements that I made, that double filtering an already filtered variable in general I told you is not equal to the original filter data in general. The exception I told you, it is in the spectral filters. Okay, so we can take box filter and see what happens. So in box filter obviously phi double bar should not be equal to phi bar, but it should be equal in spectral filter. So we will see that one. So again here the question is we are just revisiting this, is phi double bar equal to phi bar? That question we only looked into a numerical demonstration or illustration in the last class, where I used a trapezoidal rule, linear approximation and everything to show that these two are not same in a box filter. Okay, so now if I take box filter, okay, so phi double bar, okay, phi double bar is not equal to phi bar. How do I say this? Now we have this generic filter definition, we can use this. So I can say phi double bar now is nothing but integral minus infinity to infinity g of r phi bar dr, filtering an already filtered variable. So this is equal to integral minus infinity to infinity, what is g of r? 1 by delta, okay, 1 by delta phi bar dr. What is phi bar? Phi bar is nothing but again integral minus infinity to infinity g of r phi dr. So this particular thing is phi bar here, this is phi bar, whatever is inside the round bracket here. Okay, so now this is equal to minus infinity to infinity 1 by delta minus infinity to infinity, again g of r is 1 by delta phi. Now obviously this is not equal to phi bar. What is phi bar? Phi bar is what is inside this red, which is just integral minus infinity to infinity 1 by delta phi dr. Okay, so this is phi bar. This is phi bar. So I can take it here like this. So therefore phi double bar is not equal to phi bar, because there is a 1 by delta of phi bar coming up again. So even for the same filter size, obviously if you change filter size it's obvious, right? Let's say phi bar is at delta and phi double bar you are taking 2 delta, you are taking a bigger and bigger filter size, obviously the averaging will smoothen out more data, volume averaging, so obviously it will not be same, that's obvious. But even for the same filter size delta, you can see that it becomes 1 by delta, right? Phi bar divided by delta will happen. Each time you filter it, 1 by delta is coming, and therefore phi bar is not equal to phi double bar for a box filter. For a cutoff filter, or the spectral filter, okay, spectral filter. For this, the phi, I will use this cap because we are working with the wave number space. Double bar now is equal to the same thing. I can say integral minus infinity to infinity, okay, g cap of k, wave number, right? R is the spatial variable for the in the physical space. Now we are working with wave number space, k. K is the wave number, so g cap of k, okay, and then I have the phi in the wave number, correct? So this is equal to minus infinity to infinity. What is g cap of k? It should be 1, and then I have the integral minus infinity to infinity. If I take the g cap of filter, phi bar, so phi bar is now again g cap of k, phi cap dk, so is equal to integral minus infinity to infinity, integral minus infinity to infinity, this is 1 again, right? G cap of k is again 1, so this becomes only phi cap dk dk. This will become one here. Since it is not 1 by delta here, the filter cutoff filter size is 1, you are setting it, no matter how many times you are going to filter, you are going to get the same here in a spectral cutoff filter. So only this is an exception. Only if you are using a spectral filter, filtering again and again gives the same result. Otherwise, it will always give a different result. Okay, fine. Take one more note. So you may be right now a little bit confused with, okay, what is this filtering? I have to choose a mesh first, and then mesh itself is a challenge because you need to refine the mesh to see mesh convergence and everything. Now on top of it, I have filter to work with. I choose this filter. What if I use a bigger and bigger filter, right? So many parameters. So life is easy if you are in finite volume method. Filter size becomes same as your discretization. Okay, so your mesh size becomes filter size. Life is easy, no filtering operation required in finite volume method. Your discretization itself is filtering operation. So in finite volume method, that's a particular reason why finite volume method became so popular in fluid mechanics compared to finite difference or finite element. Okay, so in finite volume method, FVM, okay, box filtering is a default choice. People use in finite volume method. I told you spectral filters are used in pseudo-spectral solvers. If you are using Navier-Stokes in the real space, finite volume method, box filtering is default. And further, implicit filtering. Implicit filtering. Implicit means that you are not doing an extra filtering operation here. So what this implicit filtering means is filtering is same as discretization. That is your finite volume or control volume. Just the mesh size. So you don't have to do an extra filtering operation. That means whatever you are going to filter, that means whatever you are going to capture or calculate using your mesh is your resolved component. Each time you refine the mesh, you are capturing such eddies. So it's much easy to think in physical space. Okay, I want to capture all the eddies from, let's say, meter size to down the way to, let's say, 1 millimeter size. Then I'll put a mesh size 1 millimeter, that will be my filter size also. Anything smaller than that, eddy smaller than, let's say, 1 millimeter, will be my subgrid scale. That requires modeling. Much easier to think now. Okay, right? I mean, you of course you need to know all these concepts, what is a filter and everything. But coming down to the finite volume method, there's a big advantage. Filtering becomes same as discretization. Otherwise, if you are using any other method, finite difference, finite volume, you need to do an extra filtering operation on top of your meshing. Okay, so then all this knowledge is useful, which which filter to choose and all these things. Okay, fine. So now we move to okay, so filter types are done. Filter size is what you choose, and if it is, I told you, FEM, it's a mesh size. Subgrid model, subgrid scale, SGS models. Okay, so we'll give a little bit of one model we can try and see. So subgrid scale, SGS models. So what is the objective of an SGS model? You already exposed to a lot of modeling, turbulence modeling now. So what is the objective of an eddy viscosity model? What is it modeling? Eddy viscosity model. Reynolds stresses. So now these Reynolds stresses are associated with which turbulence scale? All scales. So eddy viscosity model is modeling all turbulent scales. So now, ask the same question here. What should be the objective of a subgrid scale model? Modeling the subgrid scale. Okay, that is the objective now here. That means you must resolve the scales that are larger than this. Then only these SGS models will work properly. You should not expect SGS model to make your predictions better with, let's say, poor resolution. Most scales you have to resolve in the spectrum I told you, right? So the energetic spectrum, inertial range, all this has to be captured by your mesh. Then only SGS models work. So the objective here is to dissipate energy. Unlike eddy viscosity model, which is modeling all the scales, an SGS model's objective is to dissipate energy. I am computing the energy in the energetic range and inertial subrange. That energy is given to SGS model, and SGS model's single most objective is to dissipate it. If it's not dissipating, your spectrum will not look good. Okay, there will be energy accumulation in the system. The code can crash, or you may get some funny results. That energy has to be dissipated out. This is being pumped into the model must dissipate. So the objective is to dissipate energy. Okay, unlike eddy viscosity models, right? So you can say here, that is, unlike eddy viscosity models whose objective is to model all scales of turbulence. Here it is only to dissipate the energy that it is being sent to it. Okay, so now what is the unknown in the filtered Navier-Stokes equation? Tau ij SGS. This looks like ui uj filtered minus ui filter uj filter. I told you already, in LES we are computing filtered velocities, that is ui bar, right? We have no access to ui uj bar. This is an unknown here. and therefore this entire is resulting in 6 unknowns, right? So this has to be modeled, right? This entire part, the tau ij SGS. So now let's take help from RANS to see whether we can help. RANS is a much more ambitious modeling, because you need to model all scales of turbulence, right? If that has accomplished something, then it is a much more simple job here, because most of the energy you are computing, most of the scales you are capturing, only dissipative scales has to be modeled, right? So it's much more easier here. So we can perhaps learn something from eddy viscosity models. So let's say analogous to eddy viscosity models. So let's say here recall EVM, where you had minus ui prime uj prime average. Averaging is ensemble averaging here. We are moving to the RANS world, eddy viscosity model, right? This is equal to Boussinesq 2 nu t Sij bar minus 2/3 k delta ij. Correct? This is the Boussinesq that we used. Boussinesq. So now this I can rewrite this as ui prime uj prime average equal to minus 2 nu t Sij bar plus 2/3. What is k? K is nothing but half of ui prime average. So I can write this as half of ui prime average delta ij. Now there is a problem. I told you indices should not repeat more than twice. So I cannot have ui prime delta ij. Correct? So I will take this as uk prime. It's a free index. It's a sum of 3 anyway. uk prime average will be sum of the 3 normal stresses, right? So this will give me essentially minus 2 nu t Sij bar plus 1/3 uk prime average delta ij. Now I can use this concept here. Okay, so analogous to Boussinesq, hypothesis, tau ij SGS can be modeled as tau ij SGS model. This is of course exact what we have written above, right? So this is the exact one. The model is minus 2. Can I write nu t? Nu t can I write, or we have to do something else here? No, nu t accounts for all scales of turbulence. We are not doing that. So I need nu SGS. I need a so-called viscosity associated with subgrid scale motion. Again, numerical argument. This is not a viscosity. Okay, minus 2 nu SGS Sij. Now where is this Sij coming from? And what is the over bar meaning here? Sij bar means in LES filtered. So this is the filtered strain rate that is available to you. This is known, right? Half of dou ui bar by dou xj plus dou uj bar by dou xi. You are calculating ui bar, filtered velocities. So the filtered strain rates are available to you. This is a known thing. Nu SGS is an unknown. We will see what we can do with that one. Plus 1/3 uk prime was there. So I am going to, that means here this should be tau kk. Correct? Tau kk delta ij. This is your closure for the tau ij SGS. minus 2 new SGS Sij bar plus 1/3 tau kk. So where we can say here this Sij bar comma tau kk both are filtered data available to you. These two are filtered variables, that is known to you. Okay, filtered variables or known, let's say, it's okay. And new SGS is an unknown, right? So new SGS is the unknown. So this is one option of modeling. We still have not figured it out what is new SGS. So for that we can say there is a small variation to this. Let's say this equation number, we call it 1 here, or I can say star. So in equation star, sometimes it's popular to replace this tau kk like using the k, like here in the eddy viscosity, but that k becomes SGS kinetic energy, not the for the whole energy spectrum. So that's popular, so that version is also used. So the equation star sometimes is written as, in equation 10, this tau kk is sometimes replaced with 2k SGS. The reference for this is in the Pope book. Okay, see Stephen B. Pope. So tau k is replaced with 2k SGS, then therefore tau ij SGS model is minus 2 new SGS Sij bar plus, it becomes now 2/3 k SGS delta ij. This is another option compared to the first. That star, equation star, is one option. This is another option where both new SGS and k SGS are unknowns. Here now, so here new SGS, k SGS are unknowns in this version, the second option you can say. And we can model this new SGS analogous to, or the like dimensional grounds that we do, right? Since it's kinematic viscosity, it has to be meter square per second. Okay, so we can say new SGS is equal to, using let's say mixing length hypothesis. Okay, so let's say analogous to mixing length. Mixing length model, that is where nu t was set equal to a mixing length followed by a time scale, which was your du dy. Okay, so therefore it becomes meter square 1/second. So analogous to this, I can say now new SGS, let it be equal to, I need a length. This length should be subgrid scale length. What is a subgrid scale length? I know the grid size. Okay, so I'm going to use the grid here itself. This is the one factor, not one factor, this is the factor which makes LES solutions not grid dependent. Grid independent solutions are not possible in LES, because the length scale, that is actually the mesh that is going in here. Okay, so the length scale has to be a subgrid length, correct? So the L has to be a subgrid length, and I am going to use CS delta. So this is the subgrid scale length or mixing length or whatever you want to call it. Mixing length, okay, or SGS length scale. So obviously it has to be smaller than delta, right? Some factor, CS has to be some decimal. So CS delta square, because it's L square, meter square, right? And the strain rate I can use, that is the resolved component I have access to. So I take help from the resolved strain rate. So that is equal to CS delta square. This is nothing but square root of 2 Sij filter, Sij filter. So this gives me meter square per second, dimensionally sound, right? So here note that this particular delta is filter size, that is a numerical length scale. So your SG, mu SGS is depending on the mesh, so it's mesh dependent, right? Mesh dependent. Grid independent solution is not possible now because you are always computing new SGS no matter how small delta is. Some contribution is going into this one. A numerical length scale has been put, delta, and Sij is the, as I already told you, this is the filtered strain rate. Okay, that we already know what it is. It has to be half of your dou ui by dou xj filter plus dou uj by dou xi. And what is the filter size delta? So this filter size delta is nothing but your delta Vijk cube root. That is nothing but your delta x, delta y, delta z cube root. Delta Vijk is the your index that you are using while coding, ijk index, and the control volume size delta V. So local grid size is being used here. Local grid size. So this is implicit box filter, infinite volume method, right? So this is what you are using. One disadvantage in this model, okay, I did not name this model. That is strange. This is actually called Smogorensky model. I left out the main thing here. Okay, so this particular model is called Smogorensky model. Whatever we had discussed so far, the SGS model part, right? So this is the Smogorensky modeling. The reference for this is Smogorensky 1963. So this precedes almost 1 decade for your standard K epsilon model. So an SGS model was already available before, and that is true that the first CFD calculations, if I am not wrong, were done by meteorologists. They were calculating the weather using the so-called very large eddy simulations, VLES or even VVLES, very large eddy simulation, because the mesh was so large, probably a 10 kilometer is your mesh size or something like that. So in those times, so they were calculating much ahead before RANS models came. So it's much earlier, 1963. And one disadvantage of this Smogorensky model is that disadvantage of Smogorensky is the model constant CS, right? So this CS value is user dependent. CS is user dependent. Obviously it has to be a fraction because the length scale has to be smaller than the delta at all. So CS has to be some value, and there are some grid guidelines you can take, or you can say it's like best practice guidelines. So for some flows it is available what this value has to be. So the CS can take, for example the value can take CS is equal to 0.065. This is in channel flows, okay, similar to like pipe flows, plane coed flows, Poisson flows, all these things. And when you are going to open shear flows, free shear flows like jet, it becomes 0.25 in a jet, turbulent jet flow. So this is the disadvantage of the Smagorinsky model. CS has to be known. If CS is known, it is straightforward. The model is very robust and stable, right? And not much calculation is required. You just have access to the filtered strain rate. You know the delta, the mesh size at any given point. CS, if you happen to know what is good for a particular flow, it's straightforward to use Smagorinsky model for the SGS contributions. Okay. Any questions on this I'll take before we move to slight variations of this model as well as other types of models, other class of models.